Hi, welcome back. In this lecture, I want to talk about PennyLane. I will give you a brief introduction of the software. PennyLane is the software that we're going to use in this course, so it's important that you go through these basic concepts with me today. PennyLane is among the most famous and the most used frameworks for quantum machine learning code development. At the heart, PennyLane consists of a core software package to implement quantum circuits. It turns out that we are going to use PennyLane to describe a quantum circuit that we're going to use in our quantum machine learning algorithms. So it comes with some quantum circuit capabilities, and also it comes with some built-in quantum computer simulators. So in order to test and developing quantum machine learning circuits, it becomes quite handy to have quantum computer simulators so we can test the results. Also, PennyLane provides some training quantum machine learning models, both with native tools embedded in PennyLane, but also through a TensorFlow interface. So we will be able to use a TensorFlow interface and programming a quantum machine learning algorithm as it is in TensorFlow interface. It can also be extended with a number of plugins to interface with quantum computing frameworks and platforms. This includes interfaces to Qiskit, that is the IBM framework, Amazon, Bracket, the Microsoft QDK, and the Google Circ. So once you installed with PennyLane, so PennyLane is a Python framework. The front end is in Python, so you can easily install with the pip install PennyLane. When you're ready and PennyLane is installed, you can import the PennyLane modules just with this simple line: import PennyLane as QML. After running this instruction, you can check which version of PennyLane you're running by printing the string qml.__version__. It turns out that PennyLane and in general all the quantum software are updated quite frequently. So sometimes some of the instructions that you will have in this course only apply to a certain version. So it's important that you have a knowledge about the version itself. To run a circuit, so for instance, we saw the different components for quantum gates and qubits. So we might want to create a circuit. In PennyLane, we need two elements: a device object that will tell where we're going to run on the quantum simulator or on a quantum computing system, and an actual function that specifies the circuit. The first step, as I said, is to define the device object, and we can do easily using this command. So for instance, if we have a circuit and we want to run it on a default qubit simulator using 2 qubits, then we can use a qml.device, a string to tell where we want to run it. In this case is the default qubit quantum simulator, and then we want to tell how many qubits that correspond to the number of wires we have in our quantum circuit. In this case, we want to have a quantum simulator with the 2 qubits. So that's the first part. We tell first where we want to run, and the second most important part is how to define a quantum circuit that we want to run. So we define a circuit defining a function, a Python function. In this function, we will execute instruction corresponding to the action of the quantum gates. And then also we will define the output of the function from the circuit. For instance, can be the amplitudes of the different quantum state or some measurement sample. Let's see an example of a quantum circuit function definition. In this case, we want to define a function called QC, and then we want to define a number of transformations on the quantum system. In this case, we're going to have 2 qubits, and then we applied a poly X quantum gate here, and then on the same, so this is the qubit 0 or Y 0, and then after that we apply another AND gate. So this corresponds to this, and then nothing. And then, as I said, we can return what is the amplitude of the quantum state in this quantum circuit. So together with the poly X, with the Hadamard gates, we can define a number of rotation gates. For instance, we have Rx, Ry, Rz, where we define what is the angle and on which qubit we want to apply. In addition to this rotational gate, we also have the universal single qubit gate U, where we define theta, phi, and lambda as argument, and then as a last argument we define on which qubit apply this universal gate. We also have control gates. So for instance, control poly gates can be applied on a pair of qubits. Remember that the control gates require to define one qubit, that is the control, and the target qubit. So in this case, we define a pair of qubits as W, where the first qubit is the control qubit and the second one is the target. So we have C naught, that is our Cx. We have Cy, Cz, and this W is nothing else than a pair of qubits. So as I said, the first wire on the first qubit, W naught, is meant to be the control qubit, while the second one must be the target. An interesting part also, we can define so-called parameterized quantum gates by an angle of theta, and that can be added to the instruction. So this, for instance, can be provided as an argument of the quantum circuit function. We reached the last step, so almost there. So we want now to run the quantum circuit itself, and we need to do things. First, we need to actually assemble. Assemble is actually to put together the device that we define as a first step, and then the quantum circuit definition that we define as a function, and the name of our function was QC. Once we defined and assemble our circuit and device, we can just run it by calling the function. Remember, the output of our function was the amplitude of the state, and this we see the results of our tensor, and we can also calculate analytically here on these slides, and we can see the actual result is correct, luckily enough. So in PennyLane jargon, the results of assembling a circuit function and the device is known as a quantum node. So during this course, we often talk about quantum node. What you need to remember about quantum node, this corresponds to assembling a circuit function with a definition and the device, that is where we want to run the quantum circuit. To streamline the circuit assembly and definition of device, we can just use a Python decorator just before the definition of the quantum circuit. So we can add a decorator at qml.qnode parentheses dev, and this will do the assembly part for us, and then we can just run it. This is also a nice way to define a quantum node by assembling both the function that is after the decorator and the device that is provided here. So by placing this decorator, it becomes automatically a quantum node. Here just an example of gate parameters in a function. So the nice thing here is that we can provide in the quantum circuit description an argument data that we can change in time. So we can also include loops, conditional, depends on the circuit parameters. So we can provide this parameter, and then this parameter can be also included in the quantum gate operation. We can also print it in graphical form, the quantum circuit, by using qml.draw method. In this case, we put the theta equal to 2, and this will give this nice output. As the output of our quantum circuit definition, we have at least 3 possibilities. We saw that we can have a QML dot state that returns the amplitude of the quantum state in the computational base. We can have a list with the probabilities of each state if we use QML dot probs, and we indicate on which qubit we want to have this probability. And also we can mimic the quantum computing device by taking the samples of measurement in the computational basis by calling QML.sample function. When we get the sample, also we need to provide a shots argument, so how many samples we want to have. This is the last slides of this lecture. Talk to you soon.